Hi everyone. In this video, which is video 2 on a series on Venn diagrams, we're going to look at Venn diagrams and more complex set expressions. The first two problems we're going to focus on involve both two sets, so there's two sets A and B, and the universal set, and some complementation or complements. So A union B, the expression on the left, A intersect B, all of that complemented. So the complement of A intersect B. The way that I do this, and many other teachers, is you sort of do it as sort of like an order of operations problem. So what region is represented by the expression within the parentheses, A intersect B? Well, A intersect B, as we went through in a basics video, is the region that is common to A and B, for the set of elements that are in both A and B. Now, complement, as you recall, is the complement of set is everything in the universal set, but not in the set itself. So A intersect B complement would be the set of all elements within within the universal set, but not in the set A intersect B. So I'll represent that in red. That would be everything that falls outside of the intersection. So everything, all of that region, all of that region. So essentially everything except for the intersection. So the region in red is the representation of A intersect B complement. Now, the expression on the right, A complement union B complement. There you go. So A complement union B complement. The way that I do this one, and again, this is the way many people teach it, is you again follow sort of an implicit order of operations. In the order of operations, please excuse my dear Aunt Sally. Exponents come before addition and subtraction. Intersection and union are sort of at the same level as addition and subtraction. Complement is more like an exponent. So what I do is I do this one piece at a time. I'll say, okay, I've got a complement. A complement, which I'll represent in this direction, is everything that falls outside of the set A. B complement, which I'll shade in a different direction, it's another exponent, is everything that falls outside of the B circle. So I'm shading this in a different direction. Everything outside of the B circle is B complement. Okay, now look at the operation in how you're connecting these. A complement union B complement. Recall that union is an or statement. This says an element is in A complement union B complement if it's either in A complement or it's in B complement. Either one would be true. So the final region, which I'll represent in red, would be, there you go, would be everything that's shaded. Everything that's on either A complement or B complement. So the final set, the set representing this expression, would be everything that's either in A complement or in B complement. So it would be that red region right there. All right, now notice that these two regions are the same. And that basically depicts one of De Morgan's laws for sets. A intersect B, quantity complement, equals A complement union B complement. The pictures don't really represent a proof, but they do suggest that this would be a true statement. One that's a little bit challenging for some students actually was the source of my dissertation, is A union B complement. So what's the big deal with this one? Again, I will do the same thing. I will represent the sets individually. The set A, I'll represent like that. So everything in the A circle. B complement, which I'll represent in this direction, is everything outside of the B circle. Everything that's in the universal set, but not in the set B. Okay. Now, A union B complement would be everything that's either in A or is in B complement. So, as we've sort of talked about, union is more or less like set addition. So the final region representing this would be everything that's shaded. So this region, and everything that falls outside. So the region shaded in red is the set, is the expression, the sort of the picture representing A union B complement. The problem that some students have, and actually many students have, is they say, well, you've got B complement, so you can't have this little piece right here, because that's inside B. B complement doesn't say you can never have anything in B. What it says is it contributes everything outside of B. This little section in here is contributed by A. B contributes everything outside of B. The final two expressions, and this will be an introduction to basically the next section of the class, which is proofs involving sets, is really a question. This is a question about associativity. Notice the symbols are all the same. A intersect B union C. If I change the position of the parentheses, does it change the sets? Or are set expressions associative? Can you group the symbols in many ways, like addition? So the question is, are these sets equal? For the first one, I'm going to, again, represent it one step at a time. It's the way I like to do it. I'll say, okay, well, what is in the parentheses first, A intersect B. I'll represent that in that direction, this direction. A intersect B is everything that's either in the A circle, is in both the A circle and the B circle. It'll be that region right there. C, which I'll represent like this, is everything that falls within the C circle. Everything within the set C. Now, the union of those two sets would be the set of everything that's either in A intersect B or in C. So if it's in one of those two sets, it's in this big expression. Well, that would be everything that's in A intersect B or in the set C. Again, it's essentially everything that's shaded. So the red region represents this expression. Let's look at the expression on the right. B union C, again, doing parentheses first, I'll represent like this. So B union C is everything that's either in B or C. So it's essentially the B circle and the C circle joined together. So that region right there is B union C. A, I'll represent in another direction, is everything that falls in the A circle. How are these two sets joined? With intersection. Intersection means that the element must be in A and in B union C. Well, in other words, it would be the region where the two overlap. So the region where it's in A and it's in B union C would be this little section, the middle section in this three-set diagram, and this section right here. Now, getting back to the question, are these equal? The picture would seem to suggest they are not. What we would need to do to actually prove they're not equal is come up with a counterexample. Show that there exists an A, B, and C such that A intersect B union C does not equal A intersect B union C. So give me the sets. A equals 1, 2, 3, for example. Give me those sets with the elements. Show that, for your example, that these two sets are not equal.